Is the RISC-V architecture ready for a desktop system? Stay in the video to find out and see the step-by-step of its configuration. We will use an OrangePi RV2 board. Its origin is Chinese, and on Amazon you only find the board. There are almost no cases for it. Once the case cover is finished, we wait for it to cool down. Then, with the wedge, we carefully peel it off the 3D printer's bed. Now we proceed to print the base. The colors of the original Raspberry Pi cases are used, the red base and the white case cover. Then we already have the components to be used: the board, the case, an NVMe disk, a microSD card, and the brand's original adapter. We extract the NVMe drive from its box. It is a 256 KB M2 drive, much faster than microSD or USB drives. This is how the printed case turned out. The models can be found on the internet and it fits very well. It has all the right holes. Now, we extract the board from the anti-static bag. We use a scissor for the cut, since the bag is sealed. It has 8 RISC-V cores, 8 GB of RAM, 2 M2 slots, Wi-Fi 5, 2 gigabit LAN ports, 3 USB 3 and 2 USB 2, and the Type-C. We install the NVMe disk on the bottom of the board. We use a screw to fix the disk correctly. A thermal pad is suggested for it. Once the disk is installed, we insert the board into the base of the case, starting with the back so the front enters the holes. RISC-V processors have the particularity of not needing heatsinks or fans. However, it is advisable to place thermal pads on them, as well as heatsinks on the processor and memory. We close the case so that it fits. In the first tests, we will not use any fan. The same way as the Raspberry Pi, the board boots by default from the microSD. We must burn the image and then activate the disk. I like rolling release distros, so the first distro to try will be BreadOS, which is a distro based on Arch Linux. We download it. According to the documentation, it is suggested to use Balena Etcher. We tried burning the image, but for some reason it had issues. You can use any application to burn the image. For this case I will use Raspberry Pi Imager, which is a very versatile software. At the end, we extract the microSD and insert it into the board. We prepare the video and power connections, as well as peripherals. It tries to boot BreadOS despite downloading the right image. The boot fails, staying in a loop and with intermittent video feed. On the official page of the board, it shows different compatible distros from OpenWRT, OpenHarmony, Ubuntu, BreadOS, and Tutorial OS. We select OrangePi OS based on OpenHarmony. We download the image and burn it on the microSD to make a second attempt to boot it. We extract the microSD after burning the image and insert it into the board. Then we connect the board to start the system on OH. This image is very stylish, boots very fast, and enters the desktop environment. We look for the option to change the language set. But when entering the configuration, the desktop environment starts to fail, doing screen rotations without having a gyroscope. As a third attempt, we return to the site and enter OrangePi OS based on Ubuntu. We download the image and burn it with the imager. As in the two previous attempts, we place the microSD with Ubuntu on the board and connect it. This time it boots to the desktop. We enter the GNOME menu that brings the default applications and the board configuration. We run the terminal and adjust the size. We are going to configure it to boot from the NVMe. We run lsblk to see the name of the disk. It appears as NVMe 0 and 1 and it is empty. The documentation suggests using gparted, but fdisk is more effective. We execute it and press the letter G to create a GPT table. Then, we press N to create a new partition. Press Enter for partition 1. Enter for the initial size, and Enter for the final size. After creating the partition, we press the letter W to write the partition table. We run lsblk to observe the changes on the disk. Now we run the command sudo nand-sata-install. We press option 4. Select the NVMe disk and press OK to continue with the process. We press yes for it to erase the disk. Then we select option 1 for ext4. After OK, it starts to configure the NVMe disk properly. Then it will copy the system files and finish configuring the disk. It took a little less than 15 minutes to run this whole task. At the end, it asks if we want to change the boot mode to SPI. We press the yes option. Then it updates the bootloader. We say yes. Then it asks us if we want to turn off the equipment. We press power off. Then we wait for the equipment to turn off completely. To verify that we performed the procedure correctly, we must extract the microSD memory and leave the board with the NVMe disk. The procedure was carried out correctly, as the system started to boot for the first time from the NVMe disk without any problem. We do a review of the panel and the GNOME menu. The next step is to update the system. For that, we must connect to the Wi-Fi network. We check the available networks and select the appropriate one. We enter the password and wait for it to connect to the internet. Now we open the terminal and adjust the font size for better visibility. We install the Neofetch package to see system information. We run Neofetch and see Orange Pi based on Ubuntu, Kernel 6.63, and GNOME 46. It uses little memory when idle. Now, through commands we verify the version of the distro, the kernel version, the memory, and disk consumed. It boots in just 21 seconds. We enter Orange Pi config, select network, then SSH, and it starts with the installation of the packages. We save the configuration. Before connecting via SSH, we run sudo apt update to update the repositories and the list of packages. We see the Huawei Cloud. Now we run sudo apt upgrade to perform the full update. In order to have the packages and the system completely up to date now, we restart the system so that the new updated packages load. We wait for it to enter the GNOME Desktop environment once again. We run the terminal, increasing the font size, and run the Neofetch command again. We see that it updated to Ubuntu version 24.04.4. Now, we do connect via SSH from another computer with the IP of the board. We enter the password and it enters at 55 centigrades. To evaluate thermal changes, we perform the installation of some package. For example, another browser like Qt Browser, we wait. At the end, we log in again via SSH. But now we see that the temperature rose to 70 degrees, a high value for the task performed. Now, to stress the processor more, we run a browser. We load the YouTube site to perform a certain load of processes and memory. We repeat the SSH login process to see the mod update. For this case, the temperature has already risen to 80 degrees with load. These temperature changes are very dangerous for the processor, mainly because it is not such a stressful task. We power off. We open the case of the board and check the temperature manually. This is to see if the thermal pad and the heatsinks work well. There is not much thermal transfer, so we better remove the pad and install a larger heatsink, direct and suitable for the CPU. When removing the thermal pad well, we proceed to remove the heatsink protector to adhere it to the processor for better cooling. Carefully and centering the heatsink, we stick it to the processor. We apply pressure on the heatsink so that it adheres correctly. We install a fan in the proper slot, but it does not turn on. We proceed to open another fan to check if it has any problem. We install the connectors on the pins properly with positive and negative. With this, we verify that the pins provide no voltage. To avoid going to the configuration, we can use the board pins. Pin 2 has 5 volts and 6 is ground. We connect, and here it worked. We proceed to change the fan. Since the second one has pin connectors and the previous one was XH254, the pin 1 is better here. Due to the size of the fan, we can only leave one screw, which is sufficient since the fan does not have any significant weight. With the fan installed in the cover, we connect the mentioned pins and verify that it has a correct operation for the hardware. It is important to place the fan with the label facing up. We must always verify that the air comes out, for example, with paper. We start the system again and wait for the desktop environment to load. Now what we are going to do is test the stress temperature. We enter via SSH and see the initial temperature of the processor. Now we have 54 degrees, which is ideal for the CPU operation. Then we run the browser again and update the mode with the run parts command and see that the temperature rose, but it goes down. We stress the system more by maximizing the window and loading a video so that the processor enters stress to measure heat levels. We return to the SSH console and update the mode. The temperature increased to 60 degrees. We update again and it dropped to 59. This indicates that the change of the heatsink and the use of the fan has left the board thermally suitable for its constant use. In conclusion, the OrangePi RV2 board is suitable for use with a system with a desktop environment and the right configuration. The use is comparable to a Raspberry Pi 5 board, with the difference that its cost is much lower. Do not miss the following tests. If you like the video, subscribe, leave a like and activate notifications to stay updated. We will see you in the next video soon.